For the solutions of these problems, I will be referring to the MIPS reference datasheet, although I won't show it. If you're interested in how I use the MIPS reference datasheet, please refer to the video tutorials on machine language encoding. So for this instruction, I know it's an add, and I look up the add in the MIPS reference datasheet, and I see that its opcode is the pair 0 and 20 in hex. And so the add is also an R-type instruction, and so we know the first 6 bits are the opcode. Then we have 3 5-bit register specifiers, followed by a 5-bit shift amount and the 6-bit function code. So with a 0 as the opcode, the first 6 bits will all be zeros, and as 20 as the function code, there's my 2 followed by a 0 in hexadecimal. The shift amount, since this instruction is not a shifting instruction, is going to be all zeros, and then we just have to figure out the register specifiers. So the destination register is going to be in RD, and these two registers are going to be in RS. So T0, if I look up on my data sheet, T0 is register 8, so that's my destination register. 0, 1, 0, 0, 0 is 8. That's also going to be the same as RS, 0, 1, 0, 0, 0. And then T4 is going to be 4 more than that. That's going to be 12. So that'll be 0, 1, 1, 0, 0. The second problem, a branch not equal, again look up on my reference sheet. I see this is an I-type instruction. So the first 6 bits are going to be the opcode, followed by 2 5-bit register specifiers and a 16-bit immediate. The opcode for a branch if not equal is 5 in hex, so that means my first 2 bits are 0 followed by the number 5, and my register specifiers are T0 is going to be in RS and A1 is going to be in RT, and so again T0 we already saw before is that bit pattern, followed by A1, which I look up in my table, is going to be 5. So that brings us to the small point of encoding the immediate. Again, for branch instructions, the target is computed as the current PC plus 4 plus this immediate. I guess the immediate shifted by 2. Or said another way, it's how many instructions that need to be skipped in order to execute the target instruction. So if this instruction, if this BNE was not a branch, the instruction that we would naturally execute next would be the immediately following instruction. And so that would be the target associated with an immediate value of 0. But instead, this branch is targeting, has the label loop. It's targeting this add instruction. And so in order for us to branch to that instruction, we need to go backwards 2 instructions. And so we want this immediate to encode the value -2, or alternatively, we want this target to be targeting PC -4. So we want to encode -2 as the immediate, and recall the way that we convert numbers into negative in 2's complement. So we're going to take the positive version of the number, so we have some number of zeros leading up. We're going to flip all the bits and we're going to add 1 to that. And as a result, 1 plus 1 is 0, carry the 1, and then we have a whole bunch of 1s. So the 2's complement representation of minus 2 is a whole slew of 1s followed by a 0. And finally, to translate the below machine instruction into a MIPS assembly language instruction, the first step is to decode the opcode. So as always, the first 6 bits are the opcode. The first step is to convert this into hex, and so I have my 8-bit set and my 4-bit set and my 1-bit set. So together that's the value 13, and so if 10 is A, 11 is B, 12 is C, this is the character D. And then the top 2 bits encodes 0D. So if I scan on my MIPS reference sheet looking for D, I see that this is an OR immediate instruction. And so an OR immediate instruction is an I-type instruction. And so again, I'm going to cut up the instruction into 3 fields, 2 5-bit register specifiers and a 16-bit immediate field. And I can go ahead and directly translate the immediate. So the bottom is a 7, this is a 3, this is a 3, and this is a 1. So the immediate's going to be the hex value 1337. And then the register specifiers, I look at the reference and see that in OR immediate, the RT is going to be the destination register specifier. So let me first figure out what register this is. And so it's the value 16 because it only has the 16-bit set. And register 16 is S0. So the destination register is going to be S0. And this register is value 0, which is the 0 register. So we are ORing this immediate hex 1337 with the value 0 and writing it into register S0.